So Sarah is running at a rate of 5 meters per second, and we want to graph, 1, the magnitude of her velocity as a function of time, and 2, the magnitude of her displacement as a function of time. So let's see if we can do that now. So we'll start by graphing the magnitude of her velocity. And we only need the first quadrant because 5 meters per second is positive, and we only care about time after she starts running. We don't care about all the time before she started running, because again, that's where we get our whole sense of delta t from. So I really could be writing just t, but I'll write delta t just for the sake of it, and that's going to be measured in seconds. And here we're going to be measuring the magnitude of her velocity, velocity vector, and that's going to be measured in meters per second. So she's running at a constant rate of 5 meters per second. So to me that just seems that Sarah will always be running at 5 meters per second. So her velocity really isn't depending on time. She's going to start off running at 5 meters per second. She's going to 10 seconds later she'll still be running. She'll have gone further. So it will affect her displacement, but in terms of her velocity, she'll always be running 5 meters per second. So we can say here's 5, and then her velocity is just going to be, the magnitude of her velocity will just be 5 meters per second for as long as she's running. Alright, so now let's graph her, let's graph number 2, the magnitude of her displacement as a function of time. So again, we only need the first quadrant because we're only interested in she's going forward, so her displacement will always be positive, and again, the whole delta t thing. So we're still measuring that in seconds, and we'll be measuring her displacement, rather the magnitude of her displacement, in meters. So when Sarah first starts off running, we're going to assume that she's starting at a displacement of 0, because she hasn't changed her position at all. So she's starting off at 0, right? Because she hasn't. It's not like her velocity where she was always running at 5 meters per second. With her position, she started off at the origin. She hasn't moved anywhere. So now let's see what happens 1 second later. So 1 second later, we know that we know that velocity. Let me see, the magnitude of velocity is going to be equal to delta s over delta t. And so if velocity is 5 and t is 1, oops, that should be an s, and t is 1, then anything over 1 is just 1, so her displacement is 5 meters. So we can graph that right here. This isn't the same scale as the other graph, as you can clearly see. So 1 second later, she's gone 5 meters. Alright, so now let's take a look what happens after 2 seconds. After 2 seconds, we can just plug in the same thing again. Her velocity is still 5 meters per second. And I'm foregoing writing the units just for the sake of time here. And so we want to solve for her displacement. But now it's going to be her displacement divided by delta t will now be 2. So again, we can solve for delta s, and so we get delta s is going to be equal to, this time, to 10 meters. So that would be up here. Oh, that wouldn't be there. I'm sorry, it would be here. And I think you're getting the idea, but I'll do one more. So 3 seconds later, again, her velocity is still 5. And this time her delta t will be 3. So we can solve, we get her displacement this time will be 15 meters. So that should be up here. So this is 5, this is 10, this is 15. And x and y are, as you can see, are on a different scale. But just bear with me. And so I'm pretty sure at this point you can see the pattern. And that is, this is going to be a straight line up here. And this will just go on as long as she's running. This is a straight line. Now, my next question is, what is the slope of this line? Well, we know the slope of this line, of any line, is going to be rise over run. So the rise is going to be her change in displacement, and her run will be her change in time. And you could pick any 2 points you want, but it almost goes by the definition of velocity that whenever if you divide her change in position and you divide that by her change in time, you're always going to get the velocity, assuming in this case, which is the velocity is constant, you're always going to get the velocity, in which case is 5. So we can say that the slope of this line is 5. And that's pretty interesting. Now, there's one more thing I want to point out. If we go back to this velocity graph, and we take a look at what's happened after 1 second. So after 1 second, her velocity is 5, and her displacement is 5. And if you notice, if you were to calculate the area underneath this rectangle right here, you would get 5, which is the height, times 1, which is the width, and you get 5. So it just so happens that the area underneath this rectangle right here is going to be equal to her displacement at 1 second. So let's verify that by checking it at 2. At 2 seconds, if we were to calculate the area underneath this velocity line, we're going to get another rectangle, still with height 5, but this time its width is going to be 2. 5 times 2 is 10. And again, that matches up to what her displacement is. So I feel it's fair to say that at any point on our displacement curve, her displacement will be equal to the area underneath her velocity curve. And I'm not going to go into more detail on this until the next video, but I want you to think about it in the meantime and see if, because in this situation the velocity was uniform. But I want you to think about if this would still hold true if the velocity weren't uniform, and if so, how could we possibly calculate that? And hint, if you don't know calculus, you won't be able to calculate it, but you can still get an idea of the intuition behind it, and I want you to think about that until the next video. So, see you then.